Hi everyone, here's our last video on astronomy. Okay, this discusses the structure of space and time. Okay, let's begin by quickly reviewing something we saw way back when we discussed physics, and that was the Doppler effect. You remember, it's that change in frequency as a source of sound is moving towards us or away from us. So down here we got a picture of the police siren, makes a particular sound, and the frequency gets higher as the car approaches you, and the frequency gets lower as it moves away. And, a motorcycle does the same thing. As it approaches you, it goes, neen, and as it moves away, it goes, nyeow. Okay, it moves to higher frequencies. As it approaches you, moves away, moves to longer wavelengths. Okay, well, back in the 1920s, Edwin Hubble, and yep, that's the same guy for whom the Hubble Space Telescope was named. This guy was looking at galaxies, and he discovered that the light coming from distant galaxies was redshifted. And what that means is that the light was shifted to longer wavelengths. And what we know of the Doppler effect is when light is shifted to a longer frequency, or any wave shifted to a longer frequency, it means that the source and the observer are moving apart. And so for almost all the galaxies that he observed, they were all redshifted. And more importantly, the farther away the galaxy was from Earth, the more redshifted it was. And so what this meant is that just about every galaxy is moving away from Earth. And the ones that are farther away are moving faster away from Earth. Okay, this cannot be simply explained by some historic event where all the galaxies were exploded and moving away from a common center. It wouldn't explain why things were moving faster as they got farther away. So instead, these observations, as well as a lot of other data that came in afterwards, led to two major theories. And one, the universe is expanding. And two, the universe began from a single point, the Big Bang theory. Okay, let's talk about the Big Bang theory first. Okay, so if you look at all the galaxies and they're moving away from us, then if you could go back in time, it would imply that all the galaxies would have started from some common center and then sprung outward from that point. And that implies that the universe had a birthday. It was born at some point. And so the Big Bang theory states that, yep, at some point in time, all the matter and energy was concentrated at one point, and then it erupted first to create the universe. And based upon the speeds that we observe the galaxies moving away from us, we can do some calculations to estimate when all the galaxies, all the matter, and all the energy too, was all concentrated in one location. And the calculations say, well, that was about 15 billion years ago. And so the theory is, well, 15 billion years ago, the universe was born, and as the universe expanded, which we'll talk about in a minute, stars then coalesced and were formed. Our sun was formed at a later date, and even later than that came the molten Earth. The Earth then cooled down and formed oceans. Okay, so like I said before, the Big Bang is just not the idea that space already existed and then matter and energy was exploded into being and then filled that space. No, that's not true. The idea is that the Big Bang theory says there was nothing. There was no space. The fabric of space, whatever you want to call it didn't exist. So that all the space itself, empty space, as well as matter, as well as energy, all of that was concentrated in one location. And it all sprung into being. And then since that time, the Big Bang, the universe is continuing to grow and expand. It's just stretching out. And so in our textbook, it talks about how the space between galaxies is stretching out. Yeah, so that's kind of crazy, mind-boggling. So I thought I would look at a simpler system like stretching a rubber band. So here we got a rubber band, and let's put some marks on it. Get our ruler out, our metric ruler, and every centimeter, let's make a mark. There's a mark at 1, 2, 3, 4, 5 centimeters away from, looks like I'm holding on to the tip of the rubber band under here at the 0 centimeter mark. And then give it a pull. Stretch out this rubber band. And now look at how far away those marks are from your thumb. So what used to be 1 centimeter has now stretched out to 2. If we stretch it out in 1 second, then we can talk about speed. So the rubber band stretched out in 1 second, and the 1 centimeter mark, well, it moved 1 centimeter to the so now it's 2 centimeters away from the thumb. And so the distance it moved was 1 centimeter, and the time it took was 1 second, and then velocity or speed is equal to distance divided by time. That's our definition of velocity, well, at least without the direction component. Speed is equal to distance divided by time. So rubber band at the 1 centimeter mark, that moved 1 centimeter in 1 second. So then the speed is 1 centimeters per second. But now let's look at the mark at 2 centimeters. Well, it moved another 2 centimeters. Now it's at 4. So that mark, the 2 centimeter mark, moved 2 centimeters in 1 second. And now look at the 3 centimeter mark. It moved another 3 centimeters. It's at 6 centimeters away from the thumb. And so the 3 centimeter mark moved 3 centimeters per second. And you can keep doing this, the full length of the rubber band. Every time you go farther away from the thumb, the mark that was previously there is going to go even faster. It's going to stretch out further. And that's because each marking separates from the next mark. That is, the 1 centimeter mark separates from the 2 centimeter mark by 1 centimeter. So every mark expands the same amount. But when you compare the distance from one end to the other, all those expansions add up. And that means the marks that are farther away are going to be moving faster. And that's exactly what we observe with galaxies. And now we have to think about, what does that really mean for our universe? Well, the fabric of space might be something like a balloon. And on the surface of the balloon are all the galaxies. And over time, these galaxies are all spreading out from each other because the universe is stretching. And it's stretching three-dimensionally. And so a balloon's not quite catching all that idea because the surface of a balloon is two-dimensional. But it kind of gets the idea across. The balloon is stretching, the universe is stretching, and then every galaxy is spreading out from all the other galaxies. So instead of a rubber balloon, here's a circle, a sphere rather, and look at the surface here. Everything's spreading out from each other. And then I found a nice little diagram here. If you think about a loaf of bread, raisin bread, as the dough rises, the little raisins inside are going to spread apart from each other. And you can pick any raisin and look at all the other raisins around it, and those raisins will be moving away from the raisin you're looking at. Okay, so that just means the Earth is not necessarily the center of the universe, right? The whole universe is expanding, and everybody, no matter where you are in the universe, it looks like everybody is moving away from you. So that brings up a question. If the universe is expanding, and the farther away something is, the faster it's moving away, is it possible that there might be a really distant galaxy that's just going to be expanding away from us at such a speed we'll never be able to see it? And let's look at that idea by looking at our rubber band again. Well, let's put an ant on the rubber band before we stretch it. And it's walking along towards our thumb. So opposite to what galaxies do. We're thinking about galaxies moving away. Well, let's make this ant move towards us. And make it move towards us at 2 centimeters per second. Nice steady pace. And before we stretch the rubber band, we're watching this ant. And once it gets to the 2 centimeter mark, boom, now it's time to stretch. Stretch the rubber band out for 1 second. And let's see where that ant ends up. Well, the ant is moving 2 centimeters to the left. The rubber band stretches out at the 2 centimeter mark. It's also going to move 2 centimeters in 1 second. So those speeds are going to cancel out. It will appear to the thumb, or an observer on the thumb, that the ant is not moving. Now what happens if we start the whole experiment over and we start stretching it, stretch the rubber band when the ant gets to the 3 centimeter mark? Well, at the 3 centimeter mark, that position on the rubber band is going to stretch out at 3 centimeters per second. But the ant is only moving 2 centimeters in that 1 second. So that means at the end of the stretch, the ant is going to be here at the 4 centimeter mark, which means altogether it's going to look like it moved away from us by 1 centimeter in that 1 second. Okay, so even though the ant was truly moving towards us, we don't observe that. Because of the expanding rubber band, it looks like the ant's moving away. And so that's what's happening with the galaxies around us. The really, really close ones, well, yeah, so if the ant is at the 1 centimeter mark and it's moving towards us at 2 centimeters a second and we stretch, well, the rubber band would have moved 1 centimeter in that 1 second, but the ant can move 2, which means the ant makes it to our thumb. And so we see the ant actually moving towards us, but it just barely made it. So it looked to us like it was moving at 1 centimeters per second. Really, it was moving at 2 centimeters per second, and the universe was expanding, the rubber band that is, was expanding at 1 centimeter per second. Okay, so only galaxies that are really close will be observed to come towards us, and that's actually true. The closest galaxies actually are observed to be approaching Earth. But everybody else, farther away, they're all moving away. And the farther they are, the faster they move away. And so the universe, the expansion of the universe has been estimated that in the last 65 million years, 1 kilometer of space has expanded by 5 meters. So that's not very much. That's pretty slow expansion. But the universe is just incredibly huge. And so, just like the rubber band, where every piece of the rubber band is expanding, and all these expansions add up, and that means objects on opposite sides of the rubber band are going to be appearing to be moving very, very fast. The same is true in our universe. Those galaxies that are about 13.7 billion light years away appear to be moving away from us at the speed of light. And for those galaxies that are more than 13.7 billion light years away from Earth, they actually are moving away from Earth at faster than the speed of light. So the light that leaves those galaxies will never reach Earth, because light travels at speed of light, and if the galaxy is moving away at faster than that, and the universe is expanding faster than that, the light will never catch up. Okay, now for those distant galaxies, 13.7 billion light years away, remember they are actually not moving themselves at the speed of light. No, if you were a person in that galaxy and you looked around you, you would see the Earth and the Milky Way galaxy where the Earth is found. We would be moving at the speed of light away from your galaxy. So every galaxy is going to look at other galaxies around them and see them moving away. And all the galaxies that are 13.7 billion light years away from whatever galaxy you're looking at will be moving at the speed of light or faster. And in fact, if we kind of return to the idea that light is redshifted, the light that's emitted by a galaxy that comes towards Earth, that light travels through a universe that is constantly expanding. And as the light travels through the universe is going to expand underneath it, and that will actually stretch the wavelength of that light, and it will redshift it, just due to the expanding universe. Okay, so that's kind of crazy, but we're not done being crazy. There's something called dark energy. Then the word dark is just referring to the fact that we don't understand it. But here's what's going on. Edwin Hubble saw the galaxies moving away from us, and that brought about the theory that the universe is expanding. About 70 years later, in the 1990s, we had better instruments, and we obtained high-resolution data from distant galaxies that showed that not only is the universe expanding, it's speeding up. The expansion of the universe is accelerating. And if you're trying to speed something up, well, that takes energy to accelerate it. So that brought about the question that somehow the universe is accelerating in its expansion. So what's powering that? What energy is doing that? Well, we don't know. We don't know the source of the energy, but we have identified there must be some energy source that's speeding up the expansion of the universe, and whatever that energy source is, it's called dark energy. So here's the idea. For some time in the distant past, the universe was moving at a fairly constant rate, and then more recently, the universe has sped up on its expansion of the universe. Astronomers have also talked about something called dark matter. And again, the word dark is referring to unknown, but in this case, it kind of is dark. It's matter that's not observable by the telescope. Or if there's any dark matter on planet Earth, we just can't directly detect it. We can't see it or use any type of measuring instrument to actually detect it directly. So how do we know it's there? Why are we even thinking about something we can't see? Well, it turns out that matter in whatever form, whether it's dark matter that we can't observe or just, regular matter that we can see, all matter creates gravity. All matter attracts other matter through the universal law of gravitation. And so it turns out that's how we think dark matter exists, is because there's some extra gravity when we start looking at the universe. And the extra gravity that we're observing must be due to some matter that we can't observe, the dark matter. And so here's a couple of pieces of evidence that suggest that dark matter exists. If you look at the center of galaxies, there's oftentimes a large concentration of mass. Just like in our solar system. If you look at the center of the solar system, well, that's the sun, and there is a large concentration of mass. Something like more than 97% of all the mass of our solar system is found in the sun. And for objects orbiting a very large amount of mass, like the planets going around the sun, the planets that are closest are going to move the fastest. Mercury moves the fastest around the sun, making its trip in 88 days. And all the other planets are farther out, and they go more slowly around the sun. Well, we should expect the same thing to happen at the center of galaxies. The stars that are closest to the center of the galaxy, closest to that large amount of mass, which, by the way, is predicted to be a black hole, those stars that are closest to the center of the galaxy should be moving the fastest. But that's not what's observed. Turns out the stars that are near the center of the galaxy are going at regular speeds found for stars farther away from the center. So what's going on? Well, one idea is that dark matter is found outside the galaxy or just on the rim of the galaxy, and it's pulling at all these stars and slowing them down. The other piece of evidence is that light can be bent by gravity, just like light can be bent or refracted by a piece of glass or an optical lens. So it turns out that matter can act like a gravitational lens. And so here's the idea. Here's the Milky Way, and we're found on that. You're trying to view some distant galaxy. Well, the light coming out of that distant galaxy, as it approaches a bunch more matter, such as a cluster of galaxies, the light's going to be bent around it. And so it looks as though the galaxy is above and below, and the light is getting refracted or bent. Just like, if you look at a cup of water, a glass of water, and the light's coming through, the light appears to be bent as it goes into the glass, into the water, and back into air again. And so scientists have calculated how much matter is required to bend the light to the degree that we see it. And then they look at all the matter, they look at all these galaxies and make an estimate, hey, how much material is there that we can see? But it turns out that the calculations run short. If you make large estimates, you still don't see enough matter to account for all the gravity coming from that close cluster of galaxies. And so dark matter is proposed to be the extra matter required to get enough gravity to explain the observed gravitational lensing effect. And of course, scientists have made some predictions as to what that dark matter might be. Well, they got some neat acronyms, something called Machos, Massive Compact Halo Objects. Well, halo is just talking about the periphery or the edge of those galaxies. And these are large, massive, but very compact objects. Something like Jupiter. So Jupiter is a gas planet. It's really big. It is our biggest planet. And there might be some Jupiter-sized planets just hanging out on the edge of a galaxy. Now we said that Jupiter has a lot of helium and hydrogen, just like our sun does, but it lacks the necessary mass to create enough gravity to compress and raise the temperature of that gas to start nuclear fusion. So essentially, Jupiter is an unlit star. And in the distance, we're not going to be able to see Jupiter, especially if it's not in orbit around another star like Jupiter's orbiting our sun. So those might be the Machos. These unlit stars are just really big, found on the edge or the halo of a galaxy, and they're just not glowing, so we can't see them. The other idea is something called WIMPs, weakly interacting massive particles. And we kind of talked about one such particle, the neutrino, when we talked about beta radiation. And as a class, these WIMPs, these weakly interacting massive particles, are subatomic particles, so particles that are much smaller than the components of an atom. And for whatever reason, they don't interact with the electromagnetic force, meaning they have no charge, they're neutral. And they also weakly interact with the strong nuclear force. So the neutron is a neutral particle, but it does interact through the nuclear strong force. It can be found or bound up in atoms, and so there's ways of detecting neutrons. Neutrinos, however, don't really interact very well with the nuclear strong force, and so they're very difficult to observe. In fact, it took a lot of data and convincing that neutrinos actually exist. So Wolfgang Pauli here was looking at beta decay, right? And that's where you take a neutron and it falls apart to form a proton, electron, and something called a neutrino. And why is there this unknown particle that we can't see? Well, if you measure the mass of the proton and electron, it comes up short compared to the neutron. And if you watch their velocities and the directions of velocities, and more importantly, their momentum, and if the conservation of momentum applies, which it should, turns out that if you add up the momentum of the electron and the proton, you don't get the same momentum of the neutron that you started with. You need a third particle to add into the momentum so that they all add up together, so that momentum is conserved. So Wolfgang Pauli proposed that the neutrino might exist because the data would suggest that we need something, a third particle. And this guy, Friedrich Heinz, or Reines, he made this one famous quote and said, "The neutrino is the most tiny quantity of reality ever imagined by a human being." He actually was awarded the Nobel Prize for his work on neutrinos. So, coming back to the dark matter, maybe at the edge of the galaxy, there are just lots and lots and lots of neutrinos that we can't see, but their mass is creating enough gravity to explain gravitational lensing and to explain why stars near the center of a galaxy don't speed up relative to other stars farther away. Well, it looks like I lied. I thought this was going to be our last video, but it's getting pretty long. So why don't I break it up into two parts? Let's tackle Einstein's general theory of relativity in a second video. I'll see you then.